Well, good afternoon, everybody, and welcome to our webinar number 38, June 2016. Our talk today is by Dr. Joshua Paschal from the University of Illinois at Urbana-Champaign. And Josh is going to talk to us about his work in heterogeneous robot-assisted measurement in data sparse regions of southern India. It's a talk that I've had a chance to read the abstract very carefully last night, and I encourage people who haven't had a chance yet to read on the email to read it now. But imagine the following problem. You live in a region that is, for the most part, a poor region in a developing country where water has been dwindling for quite a while, for a number of years. And people who, of course, depend on the availability of water need to understand what's happening. And while in developed countries, this could be done by using satellite data or manned flights, that those types of data are either not available or low resolution or not, just generally not there for the regions where Josh is working at. So he and his team have come up with novel methods to using unmanned aerial vehicles and unmanned surface vehicles to collect data about the topography and the bathymetry of the region so that the people there and the officials there can better plan their water usage and their water gathering. So I think it's going to be a very interesting talk about a very relevant problem that affects not only the region in India that Josh is working at, but many, many regions in the world where water is scarce and at a premium. Josh, he is alumni of Texas A&M here in the U.S., where he got his bachelor's, master's, and his PhD. More recently, in 2012, his PhD in computer science and engineering. And currently, he is at the University of Illinois at Urbana-Champaign. But Josh is a multidisciplinary Renaissance kind of guy with multiple appointments that span from biological systems to genomics and computational science and environmental engineering. And Josh is developing a number of technologies that combine robots in the air, on the ground, and in the water or on the water with machine vision to better understand the world, collect data, and improve how humans use and affect the natural world. So with that, let me ask people just one more time, make sure you go on the join me list. There's still a few people just called viewer. Please click where it says viewer and change that to your name. And one more reminder, please mute your phone or microphone right now. Let me find out how to do that myself. And with that, I'm going to present the presentation rights to Josh. All right, we're good to go, Josh, and I'm going to mute myself so I don't disturb you.
All right. Can you see my screen?
Yes.
All right, and everyone can still hear me okay?
Yes.
Great. Well, I'll go ahead and get started and make sure to try to keep us on time here. So it's great to be with you all today. I really appreciate this technical committee and the opportunity to share some of our work here on the webinar with the group. Thank you for the kind introduction of our work and of myself. And before I get started with what I'm going to be talking about, I just wanted to point out that this is a really great collaborative project between myself and a couple of very great people at what they do. Sierra Young, who was my master's student here at Illinois in civil and environmental engineering, this was her master's thesis. So I'm presenting basically a subset of that. She's now a PhD student and a newly named Department of Defense Science and Engineering Fellow as a PhD student here at Illinois in civil engineering. And I also worked on this project with Sally Thompson, who's an assistant professor at University of California, Berkeley, her student Gopal Penny, who's a PhD student there at Berkeley, and then Veena Srinivasan, who's a fellow at ATRI, which is the Ecology and the Environment. A great collaboration between Illinois, Berkeley, and ATRI to address a mystery in southern India of drying watersheds. And in trying to get to answers to this mystery, we're using robot-assisted measurement technology to try to answer these questions we'd like to ask. So that, as was mentioned before, the title of my talk is Heterogeneous Robot in Data Sparse, where they have not a whole lot of data, and there isn't a lot of, in many cases, economic resources to pursue data gaps, and in many cases, just getting the data at all. So I want to start by talking a little bit about the region in which we were working, the Arkavathy Basin, which is geographically in the southern part of India, on the subcontinent there, and it's more close detail geographically with Bangalore Basin is a sub-basin of the Kaveri watershed south of the Krishna watershed. And this is just give you an idea of how everything is connected up. So the area highlighted in red is the area where we're most interested in. Hydrologically, and I'll talk a little bit about the hydrology because in addition to doing robotics work, I'm actually formally in the environmental hydrology and hydraulic engineering group here in civil and environmental engineering. So we're, as Marcel mentioned, we really try to approach things in a very interdisciplinary way. So if that includes developing or modifying or repurposing, robotics technology to answer our science questions, that's what we do. So hydrologically, I can tell you, we're interested in this area because its proximity to Bangalore. Bangalore being a very large city in that part of India, and its water sources are very critical for essentially drinking water. And as we'll see, for a lack of water in either one of those cases could be very critical and damaging to the economic development and economically prosperous area, as we'll see. So hydrologically, you can see the interconnectivity of rivers, but Bangalore is kind of right there in the middle. We can go down a little deeper to see where the headwaters are relative to Bangalore. Actually seeing the problems. That breakout there, the TG Holly catchment, is where we're starting to see some of the problems that the drying is coming from. Just a little bit more zoomed in area where we were actually working last summer. And I should mention, well, my student Sierra spent about 4 months there last year as part of an NSF project that Sally and I had. I was there for about a month, but that was when the majority of our data collection happened, and it was in this general area that you see here where a lot of the field activities with robotics happened. So let's get to the mystery. So I talked about reduction in availability of water, and there's been declining flows in the Arkavathy Basin that began really kind of in the late 20th century. And what happened is when you began having these declining flows in the Arkavathy River, you started to get a shift and a reliance on Coventry River for water supplies. The problem is, and we can look at some of the numbers here, so you can see here the TG Holly inflows, and as I've one of the big major headwater areas, the inflows coming in have dropped, as you can see numerically, substantially between, let's say, 1940 and within the last few years. But we don't exactly know why. There are some hypotheses that we're going to get into. But you can see down to 25%. That's fairly substantial when you have a region that's relying so much upon the water sources for agricultural uses as water. So we don't know why, but we have some ideas. Now, it's worth showing you, and my voice is kind of breaking up. Please let me know if there's this network, but I might be able to fix that. But we'll press on. If it gets really bad, just send me another note. But I appreciate it. You can see here, mostly is cropland. And when I talk about cropland, I mean traditional corn, but there is a transition, as we'll see, going from traditional crops that were more sustenance-based crops to cash crops, crops that'll just economically result in better outcomes for individuals. There's a lot of, as you can see there, red with the built-up land, urbanized area. Okay, so that's what we're dealing with, agricultural and urbanization. So the hypotheses that we're investigating here, and there are many. The first one is that there are changes in the rainfall patterns, that something must be happening, climate change, global warming, that type of thing. The amount and intensity of the rainfall that would be changing, causing this drying in this area. One hypothesis by researchers that are in that area. There's being that is being just evaporated close to higher temperatures. So that a third would be declining base flow due to groundwater. Surface water availability may cause people to capture more water through water. Think about if pharmaceutical plant, are chemicals hypothesis. And then the two remaining ones change and from traditional crops to, in the case of what we're actually seeing and as we go along, a shift in land cover to plantation.
Hey, Josh, can I interrupt you just for a minute? Josh?
Yes.
Your voice is cutting in and out.
Okay.
You're connected through the internet, correct?
I'm just on the wireless network here.
I was wondering if it would be too cumbersome for you to call in using a phone.
I can dial it up here real quick and then switch the audio off, and we'll see if that works a little bit better. Could you real quick?
Yeah, can you repeat that?
The time that
Yeah, you're really cutting out. I'm missing you. I'm losing you.
The telephone.
Okay. So the number is, can you write it down?
Yes, I'm ready to dial.
860-970-0010, and the conference ID is 1.
Conference ID and press the pound.
183
895 025.
You will now be placed into the conference. This call is being.
Now you have to turn off your internet.
Okay.
So on the Join Me app, at the top left, there is a there's a sign for like a phone. You click on that and you choose call by phone.
Okay, can you hear me okay now?
Yes, a lot better.
Okay, great. And I think I've satisfactorily gotten rid of the audio connection there. As long as you can hear me okay now, right?
It is a lot better. Thank you very much.
Well, good. All right. So, is there anything that I should need to repeat up to this point, or has been, I know I've had some bulleted points on the slides.
No, I think we're good. I think we're good. We missed a few words here and there, but we can understand everything. But the cutting was starting to get annoying.
Okay.
But now it's perfect. Thank you.
Can I close this little box up here on the right without it cutting me off?
We don't see any box. It's on.
Oh, okay, great. Then that's just on my local computer then.
Yeah.
All right. I didn't want the join.me to interfere at all with the slides. But if I see it.
Yeah, always see the slide.
Okay. All right. So I'll just pop back here to the hypothesis slide very quickly, and as long as you can still hear me okay, then we'll go ahead and just summarize that. So the land use changes is one hypothesis, and then finally the fragmentation of the watershed. Now the important things to remember, I think, on the final two are we need some method of observation for that, and that's really where the robots are going to come into play. So quickly, just looking at some of those hypotheses, I'll go through very briefly. The changes in precipitation with regard to the amount and intensity, what we've studied and learned is that it really hasn't changed at all. So any kind of influences of climate change or expectations of reductions in precipitation that may lead to lower flows, whether they be normal surface water flows, base flows, that's not really a problem. So cross that one off the list for investigators. The increasing evapotranspiration due to increases in temperature, again, a climate issue, at least over the last 50 or some odd years of the data, it's not something that we're seeing as being a problem from the data collected in those regions. Declining base flows, potentially, as we see here in information put together through well census activities, for a couple of the subcatchments in the Arkavati River Basin. So what we see here, I'll just point out quickly, is effectively a shift from reliance on surface waters to bore wells or groundwater wells as it relates to percentage of irrigation sources. So we are seeing that. The main issue being also we don't actually always know where somebody puts a groundwater well to irrigate their crops on their land. So having some method of observation there even to make that determination is going to be very important for us. The land use change, as I mentioned, the shift from traditional crops to increases in eucalyptus plantations. As you can see at the graphic there, over the last 30 some odd years, there has been an observable shift as it's been able to be identified by local persons in the area. And I think it's worth mentioning that scientists, investigators in this region, you have Indian Institute of Science at Bangalore, and these are world-class people, but there's only so many people to do the scientific investigations. So being able to have observational measurement tools for both scientists, investigators, and even citizen scientists is very important. As we go along and talk through this talk, I think it's very important to remember the economy of scale. There aren't tens, hundreds, millions of dollars available to do this type of data collection, so we need to think about price points as well. But land use changes to grow the economy, and that's what's really driven this area, is farmers make a lot more money when they can grow eucalyptus, but eucalyptus take a lot more water, and it's quite a different farming practices. we'd like to be able to do those observations too. And then finally, just the general fragmentation of the watershed, which gets us into sort of part of what we think the mystery is, which are these tanks in India. And I'll show you an example of what the tanks are, but in the T.G. Holly catchment alone, we're able to identify 617 different tanks. And when I talk about fragmentation, that may be something like a check dam where somebody's dammed up a river or part of a tributary, or just roads or bridges, but tanks, which I'll show you here in a little bit. So when I talk about tanks, tanks are essentially either natural but often man-made reservoirs that act as methods of control for farmers in the regions for irrigation purposes. And the thing is about these tanks, they act as sort of capturing devices for water that might naturally flow through the region down to, from those headwaters down to Bangalore, where we're most concerned about, and either just downstream. So if we're able to determine what the volume that could be of water that could be stored in these tanks, then that's going to help us understand recharge, because the water as it might be stored in these tanks may contribute to groundwater presence, and certainly it would contribute to stream flow, because water coming in, if it's not held onto, then it's going to continue to go downriver, such that other people could use it. So tanks in the big picture are going to be very important for us, and we'd like to understand those, but there's no information whatsoever really on these tanks from a geomorphologic perspective, which is to say how much water can actually be stored in them and how do they change over time. The way that you would get this information now would be to do something like fly a plane and use LiDAR to get a very high resolution scan of these tanks. The problem, and I think we're probably in this community all familiar with LiDAR, so I won't go into great detail about how it works and that type of thing. But as you know, LiDAR flights can be expensive. They're infrequent. There was one done for this catchment, but it was maybe 15 years ago, and it was a very small area. The other problem is that that would get you the surface, but if we're dealing with a reservoir, you're not going to get subsurface unless you're using a special kind of LiDAR. So you'll see everything above the water, but you wouldn't exactly see how much water would be, or what the topography would be below the water surface. You wouldn't get that bathymetric information. And so in the big picture, this existing practices don't really give us any improvement towards the sparse data problem in a region like this in southern India. And what we really need is a low-cost, high temporal resolution measurement technique for these tanks that are in such large number all through just this one watershed alone. So the way we approached the problem was to use small unmanned aerial vehicles. I give you some examples there. On the left-hand side, those are some of the more larger, probably a little bit more popular platforms that are used by law enforcement. In my career, I've used the air robots, the Dragonflyers, Ariane Scouts. These are, used by military. They're used by law enforcement, Seaburn community. They have high commercial visibility. They're very good. They're a little pricey. We've worked with 3D Robotics out of California to put some platforms in the field that give us a very robust platform and good capture of data for what we need. Remember, this is a place where $500, that might be available, but if we talk about some of the other platforms, $50,000, $100,000, that's not something that's going to be accessible to people once we've studied the region, but we'd like to have a continuity with investigators there and citizen scientists to keep collecting data. So the platforms that we used in India were those that you see on the right from 3D Robotics, the Iris, the X8, and we used the fixed wing sometime, but to be perfectly honest, we ended up using the Iris most of the time. So I use the word heterogeneous. So we're not using only unmanned aerial vehicles to go around and capture imagery. I'll talk a little bit more about how we actually collected the topographic information from these tanks. But we're using also small unmanned surface vehicles. This is one of the other areas of research that I do. And one of my students, Saki Honda, has done some work on this, looking at more of the human-robot interaction for unmanned surface vehicles. So on the left hand, you see there unmanned surface vehicles, and these are essentially our robot boats. And there are several out there in the community, both research and commercially. As it was mentioned, I came out of Texas A&M, and there was an unmanned surface vehicle there. And some, to be perfectly honest with you, these are great platforms, but they're kind of expensive. Some up in the $500,000 range. That is not always the case. I know there are other platforms out there that are a good cost, but what we decided to put together here at Illinois was our own little version of unmanned surface vehicles, and we did them for about $300 to $500. And they're able to, as we'll see, capture relevant information for doing this type of mapping and data fusion. So what we used in India were the boats that we built here at Illinois that allow us to do visual sensing and bathymetric mapping. So big picture, our robot-assisted data collection objectives were to firstly just demonstrate the ability to use these low-cost mobile platforms to collect data in a reasonably accurately and efficient method. We wanted to do some very comprehensive topographic and bathymetric mapping of some different chosen sites. There were 3, Hadanahali, Esamgolahali, and I always mess this one up, Neelamangala. And what that means is the above water and below water fuse together at a reasonable level of accuracy for a really low cost, certainly not in the tens of thousands that it might be for the LiDAR. All right, and what we wanted to do was to go ahead and capture what those storage volumes would be if they were full, those tanks, and what that would be available to farmers and those who wish to turn it into drinking water. So that was basically our objectives for this study. In our general workflow, we're using the UAVs to capture the areas that are dry. We capture geotagged aerial imagery we used a Sony camera that had GPS tagging that captured HD level video. We processed these images into digital elevation models. From the USV side, we captured in the wet areas geotagged images that gave us depth readings. We interpolated these gridded points into a 3D surface, and at the end of it, we were being able to use like a geographic information system. Sierra was able to write an algorithm that fused these data sets together and was able to generate a complete surface to tell us what those stage storage curves were, and that's what we were very interested in hydrologically. So here are a couple of examples from the UAV flight imagery. We were able to fly in these areas. Kind of the sweet spot for flying was about 50 feet, but in some cases we flew higher. Most of the mapping we did, and you can see sort of the heterogeneity of the environment where we had a lot of pockets of water. I think it's worth mentioning at this point that what you see there, those little pockets of water, are where people have actually gone in and dug out areas that they could store and divert water from or pump from. So we actually have human-induced influence on these storage tanks that the land surface is going to change over time. And having a high frequency of understanding of how that storage relationship might change is very critical for this region. What you see there on the left, those little pockets of water, may not have been there a couple of months before. But depending on how large they are or what kind of erosion or sedimentation that might be occurring, understanding how this landform changes in time is going to be very critical for managing the water resources. So these were just some examples from the UAV flights that gave us the dry land. We're able to basically use an in-house software package to translate that into a 3-dimensional color image to give us the topography. So this is a result of the UAV image processing results. So this is Sierra, my student, and that's her mapping out the subsurface areas with our USV. And I should mention that as we went through the mission ops, we had predefined flight plans. We essentially gave the UAVs the waypoints. It was actually very similar for the boats. We had the same onboard guidance system where we were able to task it to go ahead and search out an area and collect those, either both images or depth readings. All right, so just an illustration here on the USV data capture. We We have a hacked up version of a fish finder that's about $60 on Amazon.com, for lack of a better way to say it. We basically hacked it up and grabbed the signal off of it. So that's when I talk about these boats are really low cost. They very much are, like, under the $500 price point, and that's really great, because in the worst case, if we lose one or we lose a sensor, or alligator eats it, whatever, it's not a big deal, very easily replaceable. So it's just an example here of data points that we gathered. So this gives us all the information below the surface of the water. And what we're able to do was develop that storage volume relationship, so we can relate the depth of the tank to the volume of the water that could be realized if we had full precipitation in it. And that's what would be available to somebody for surface water irrigation and that. And the beauty of having a bit of a process like this is that we're able to visualize what that filling in of those storage tanks are in a very easy way. I'll show you a couple of more illustrations of what we were able to capture there with both the boats and the flying robots. But in terms of cost, we're talking under $1,000 for one time, and then every other time, that's the cost of the equipment. And then every time you go after that, it's basically just the cost of the time of the person. But in terms of data collection, maybe like an hour. Somebody can throw it in the back of a car, drive out there, capture all this information, and the processing time, it's maybe in the worst case, when we had very large areas, a few hours. So that's not a big deal too. So being able to result in something that you're seeing here, which can make a very compelling case for policymakers, water resource managers, anybody, just the general public, being able to produce this at this cost, at this speed, as many times as you want to, and be able to present it in a visually compelling case like this, to know this is exactly about what you would have, and to be able to see what it would look like is very helpful for the region. So here's another stage storage relationship for Hattanahalli. This is the UAV data. I think the one I showed you was the fusion of the UAV and the USV. This one is for Hattanahalli. This is just only the UAV data, because this tank was completely dry. And again, we can see some nice visualizations based on the numerics that are there. So let's get into some of the validation. All right. Where we were in terms of the validation of the result, we sent a team out to take hand measurements to see how close we actually ended up. Because you can go out and collect all this really great information about everything and be entirely wrong. So having validation points to compare your elevation data was very important. And so where we were on our bathymetry validation, we had GPS tag bathymetry points that were collected approximately 5 to 10 meters apart, randomly throughout the areas in which there were water. We referenced the bathymetry to a common datum. We then took the values from the digital elevation model that we had extracted for each of those same GPS data points, and then we did a point-by-point comparison of the elevation values. So on average, the UAV elevation values were within about 20 some odd centimeters of the GPS data for the Hattanahalli, and that's also with an accuracy of where we were on the measurement technique of about 1.5 centimeters. And it was about 0.4 meters for SM Golahalli. So that's the UAV. And where we think we are at on that, I think the last thing that I'd say about that is that given the cost, it's not exactly that 1 centimeter level resolution that you might get with LiDAR, even after some really good filtering, but the cost differential and kind of the nature of the environment to change and shift a little bit, hydrologically, 0.27 meters and 0.41 meters on a measurement that somebody would likely do with a measuring stick or something like that over a large area like this, it's actually pretty good. So in engineering, we kind of talk often about what's good enough. This would certainly be good enough for what we were doing, and then when you figure in the cost, it's pretty good. So I want to talk for a couple of minutes about opportunity costs. So in this particular area, when we talk about agricultural use, the reason why the difference between the surface water and the groundwater matters is if you're growing something like maize or nuts or paddy, you have rice, what have you, it's a big rice area, using surface water that might be stored in one of these tanks with the fact that they are dry being bad, you're only talking about a cost to a farmer of about, in terms of U.S. dollars, about $1.30 for corn up to maybe like $3.75 a hectare for rice. But when that surface water is not available to you as a farmer, then you have to put in a groundwater well. Now, when you do that, you can see the cost per hectare increases substantially for not having available to you the water that would be stored in that tank. These numbers are quite profound and could be quite impactful for the economic growth of this general region. A couple of the numbers that I want to share with you in terms of infrastructure costs to the farmer, and this is where really sort of the socio-hydrologic issue comes up. So if we talk about putting in a bore well, which we saw transitioning earlier on in one of those slides, the average cost in U.S. dollars could be anywhere from $300 some odd up to $750. Here's the problem. The frequency of the wells in this general region is about 50%. And the average life of a groundwater well is about 5 years. So what we basically say from this information, given the fact that the average yearly income of any agricultural household in Karnataka, that's the area of the Bangalore area, anywhere between $585 to $780 a year in income for a household, that about 1 every 5 years, if they have to do a groundwater well, they're losing an entire year of income. And that's profound. And so being able to understand the lack of water available to someone in a region in these tanks and what would be available to them normally, and trying to isolate and identify where the water is, where the water is going, how it's being used, that type of thing. But even just in the first place of what should be available to someone, that's really getting at the heart of filling the data gaps. The only way we can really do this very well is by capturing information through this type of robotics technology and being able to demonstrate the technique and have it being used more ubiquitously by investigators and citizen scientists in the area. Where we did this study, we only mapped a pretty small area. We're talking thousands and thousands and tens of thousands of hectares that could be mapped, but it can be done now because we've demonstrated the use of this technology. We've demonstrated that it's pretty accurate, pretty efficient. The cost is something that is certainly attractive to those in the area, and then I think furthermore, that general region is what I like to think about a little bit like the Silicon Valley of India. When we were over there were a lot of technology startups. So when you talk about the advancement, improvement of technology, just being able to give somebody a platform in which they could add more sensors or utilize the data in new and different ways also creates economic opportunities for people in those areas. And so while there have been some major stakeholders like IBM, Smart Cities, and Microsoft, and other individuals over there, it's a real opportunity for someone, if they could start a company or a business by being able to provide this information to municipalities at the end of the day to help make better decisions for water resources planning and management. So that's the big thing. I think in the big picture, what I think the contributions of this work are, and it's, again, this was the master's thesis work of Sierra, and we've been there for 1 year, and we're going to continue to do activities like this. But we've basically demonstrated that we can very successfully fuse the topographic bathymetric information using a couple different robotic platforms at a very low cost. We know how much water should be available to people now in these areas. So if they are dry, then we know how much surface water is being captured and diverted elsewhere, and what impact that might have on the groundwater recharge. And I think it's probably worth mentioning, if we're not getting groundwater recharge in the area, if you're digging a well, then you probably got to go a whole lot deeper to capture that well. And that's why we see that 50% well failure, because if we're not getting recharge out of those tank storage areas into the ground, then you're just going to have to dig a whole lot deeper, and that's going to cost more money. And if you dig down and maybe your well operates for a year, but you don't get the amount of recharge in the next year because the tanks are dry, then your well's going to fail, and then you've lost that whole year of income, maybe more frequently than 1 out of 5 years. So I think, in conclusion, just being able to provide the information on this level of spatial scale at that temporal frequency at the cost that is accessible to persons in the area who are trying to manage both their economic livelihood as well as, policymakers, planning boards, council representatives, things like that, it is really the big victory in demonstrating what we did over there in India. So in terms of next steps, I think what we'd like to do is have a higher degree of automation between the fusion of the data of the USV and the UAV. We have some nice automated algorithms that do that for us, but it would really be nice to just pull off a SIM card of each of the vehicles and press a button, and out comes in a certain amount of reasonable time a finished product. So automating some of these heterogeneous streams of data would be probably a next step. And then actually doing a more scientific per data point cost and time analysis on the collection method against standard practices. I can tell you that LiDAR might cost $15,000. I can tell you that it probably cost us about $1,000 to do this, but to do a fairly rigorous economic analysis on that would be, I think, useful in terms of scientific communication, whether it be in the water resources community or the economic planning and management community. To actually have that as a scientific comparison would be a good next step. And we're efforting that as we go along with some of the more economic data that we've shared with you. We have a little bit more work on that, but it's not exactly a number that I'd feel comfortable sharing right now. We'd want to feel a little bit more confident in that. So with that, I'll just acknowledge that we were able to do this with the very generous support of the National Science Foundation. As I mentioned, Sally and I had a Creating New International Collaboration grant that was active last year, and certainly the supports of our institutions, Illinois, the University of California, Berkeley, and ATRI. So that's that's the information that I'd like to share with you about our expedition in India to do robot-assisted data measurement to try to fill the sparse data gaps over in that region, and try to help the people out a little bit and give them technology that they can help plan for a better environment and a better economy. So with that, I'm happy to take any questions. I assume everybody can still hear me.
Yes, we can. And Josh, thank you very much. It was a very interesting talk. And I imagine you guys had a great time traveling to those regions in India and getting to see those real world problems and applying robotics there. And
I told Sierra this was her first of course, she was a master's student at the time, but you truly, I've worked in India for many years. There are great collaborators there. The thing that I tried to convey to Sierra was, I mean, so my background was disaster response robotics, and so field robotics, and what I tried to convey to her is, you really don't truly appreciate the problem until you're quite literally and figuratively standing in the river, and to try to understand what's going on using the most efficient engineered way possible, the most optimal way possible. It creates a whole new view of problem solving. And so being able to actually go there and have that experience gave us a lot of good experiences and ideas. So for sure.
Yeah, we talk about field robotics. This is the real field robotics.
Oh yes.
We have one question from Zach. I'm not sure if you already addressed this.
Okay.
It's on the chat panel. As you were going through the talk and looking at the UAV data collected versus the USV data, he asked if the data suggests that the USV has little impact, or I suppose less impact than the UAV.
In what way?
In what way, Zach? Can you go back here on the chat window, or just unmute your phone and ask?
Yeah, sure. This was on the slide with the first plot showing the UAV data merged with USV data and the UAV data alone for stage versus volume, and it just looked like those two curves were very similar to each other.
Oh, sure. Oh, I know what you're saying. Okay, so in areas in which maybe there wasn't a, let's say for example, in areas where I think volume-wise it was quite substantial, a quite substantial amount of dry area, then the USV volume-wise would have contributed very little. But being able to do just the capture, so for example, if the tank had been full, then we would have been able to use we would have relied more upon the boat to capture that. And then the boat would have had more of a pronounced effect on the actual volume stored. But that's a great observation. In those areas where the curve wouldn't have shifted very much, it just means that there were areas that weren't very full with water, because the tanks were dry, right? But there were pockets of water. So those contributions wouldn't have contributed significantly to what the storage curve were, but it doesn't mean that they weren't still there. And if those areas were being modified or dug out as additional repositories of water, then we wouldn't have known that if we wouldn't have captured that bathymetric information.
Okay, thanks.
Sure.
So Josh, what's next? Are there regions in the world that need this technology, or other environmental/natural problems that could be addressed with the technology?
I think our main focus, and gosh, we'd love to go a lot of places, but I think that because of the relationships that we've been able to establish with the University of Agricultural Sciences in Bangalore, which is a state university, and Indian Institute of Science in Bangalore, that general region would basically keep me busy for the rest of my career. As far as where else to go, certainly in areas where drought was an issue. I think that certainly there would be areas in Africa that could probably use the type of technology. I think that the way in which to best look at it is where might there be economic areas that wouldn't be able to afford high data point prices that would benefit substantially from understanding more about the natural and human influenced environment. So that's more in the developing world. I think that you might say, well, what's the win on the boats? How can I deal? Where can I use this information in the United States, in the state of Illinois, something like that? So I have a a colleague who's interested in looking at temperature fluctuations at outflows from power plants in rivers, because waterways are public, right? So you can, I apologize, I thought I had a slide in there that addressed the sensor payload that we had in there. So it's not just the sounding, it's not just the visual imagery, but we capture pH, temperature, dissolved oxygen, we can take water samples, we can do all of those kinds of things. And so if you're interested in water quality in addition to water quantity, that's certainly something that's available to you. So any type of environmental monitoring, I was part of, I can give a couple of examples. I was part of a rapid team that around the same time when the earthquake in Nepal happened, and they were interested in contamination of surface waters. So the same boat technology could give you some information about any kind of underwater mapping or water quality in an area where there's been a disaster. I mentioned the power plants. I've engaged with a lot of municipalities for inspection, but also then mapping for sedimentation in the Washington, D.C. area, lakes where you have inflows, where you worry about sedimentation and where dredging might need to happen. You can use those the same type of mapping technologies where we develop these stage storage curves can tell you how much sediment is filling in a lake or a river that you might be, it might be more difficult to get it otherwise, or it keeps someone out of harm's way. The UAVs are a little trickier because you deal with federal issues. The boats are, in general, pretty safe because waterways are public and they can carry a higher payload. So I myself like to work with the boats. That's kind of where we're focusing a lot of our efforts. But in areas where there's sparseness, in areas where that would be very hard to reach, having a price point, and I'll give a plug for, a lot of what we do is human-robot interaction. We make our own robots, but we try to make them very easy for people to use, as easy as being able to look at pictures on your iPhone and leveraging those affordances to allow you to do that. I think the two barriers to the adoption of robot-assisted technologies and having ubiquity, I think that we all desire, is the cost and the improved human-robot interaction. It has to be affordable, and it has to be reasonably easy to use. And we saw the same thing with personal computers and calculators and all this kind of stuff. So for me, that's a little bit of a soapbox issue, but that's why I work on robotics in the way I do, because there are many people in the world who need this, who would benefit from having this information, and being able to afford it and being able to collect it and then spend really their time analyzing the data to be able to ask and answer questions, I think is really the critical thing. So those are my thoughts, I think, on that type of question.
It matches really well with what we learned in our agricultural robotics program when we developed autonomous orchard vehicles.
Yes, I'm familiar with that one, yeah.
Exact same thing. They have to be useful, collect the data that's needed, perform the operations that are needed, but they have to be affordable and easy of use by people who don't have a college degree most of the time, right?
Of course. If our goal is adoption, it doesn't matter who they are. It could be fire rescue, farmers, real estate agents. It doesn't matter. It's cost and accessibility.
Completely agreed.
Yeah.
Any other questions, anyone? I think we're good. Josh, it was a great presentation, great work. Thank you very much.
Thank you. We of course, I'll just drop one final plug for our TerraMep project. That's our rapid mobile agricultural phenotyping platform that I know many in the community are perhaps working on the same Department of Energy project in different ways. It would be great to come back and share some of those results. We've started doing the field trials on that ground platform, but to be able to come back in some months and talk about that would be a great opportunity. We love to share any of the field activities we're doing with robotics. So.
The invitation is being made right now in real time. You'll be more than welcome.
Excellent.
We would love to hear about those results. Thank you,
Yeah,
Josh.
for sure. Thank you.
Everybody. And,
all right. Thanks, everybody.
Have a great afternoon. And next month, we're going to have a talk by Professor Gökhan Bayar from Turkey about his work in autonomous orchard vehicles, autonomous agricultural vehicles, and in particular, the issue of driving those vehicles in autonomous mode in muddy terrain when the wheels slip and how to control for that. Have a great day, and I'll see you next month. Thank you.
Thank you.